Hi everyone, in this video I'm working through question 15 part B of the 2020 Extension 2 trial exam from Ascham. So it's a two-part question, so as normal I'll work through each part in a separate video, and here in this first video I'll be focusing on part 1. The setup to the question is we're told we're given a function fx, and then we're told the graph of y equals f dash x is sketched below, and we've got this bell curve. We're told the graph y equals fx passes through the origin, the point 0, 0, and we're told that the inverse of fx is gx. And then part 1 of the question wants us to sketch the curve y is equal to fx. So fundamentally we've got this curve of the derivative. How can we make use of what we see with this curve to then work out the shape of the original function fx? So yeah, let's take a look. So to help work through this question, I've redrawn the sketch of the derivative f dash x, and I've noted some of the key points. We're told fx passes through the origin, and we're told a definition of a new function gx being the inverse of fx. But for this part 1, we're not really concerned with gx, we're just focused on fx, and we want to sketch it up in this axis here. So I think the first obvious point to plot on our curve is this origin, since we're told that this function that we want to sketch passes through the origin. So we know that's going to be a point on the curve. And now what we have to do is essentially reflect the general shape of the curve. There's not a lot we can know for sure, given we're only told the derivative, how the derivative acts, but there are some things we can work out. I think the first thing worth noting is that when x is equal to 0 here at the origin, what we see is that the derivative is exactly 1. And what we know is that means the tangent of our curve is 1, or in other words, the rise over run is 1. So at this point 0, we've got a curve that we kind of know hits this angle, this 45-degree angle at the origin. So I think that's something worth kind of keeping in mind as we sketch it up. The other thing worth noting about this derivative is that it's always positive. So if the derivative never actually hits 0, then we know that there aren't any minimum or maximum turning points, because we know that the turning points of a curve occur when the derivative is 0. So we've got no points where the derivative is 0. Essentially, the derivative is always above 0. So in other words, the curve that we're going to draw, we know always has to be increasing. So as x gets bigger, we know the curve must get bigger. And as x gets smaller, we know the curve must get smaller. So that's something we're going to have to make sure we reflect. And even more, something else we can kind of note is that the steepness of that gradient gets smaller and smaller as we get further away from the origin. So a smaller steepness, another way you could describe that is the curve gets shallower. And its kind of steepness eventually is approaching 0, which means it kind of approaches going horizontal, but it never really gets there. So that's the key things we need to note on this curve. It has to be always increasing, and it kind of has to be steeper closer to the origin than it is further away from the origin, noting that the steepness is always kind of less than 1. So we've got this 45-degree angle, and we don't have it increasing at a steepness greater than 45 degrees. It actually increases at less than 45 degrees, getting shallower and shallower as we get further away from the origin on either side. So I guess if I start from the origin, we can kind of say the curve we know is going to come up, and it's going to kind of plateau out, and eventually it will get very, very close to horizontal, but it never actually hits kind of being totally horizontal. Now kind of coming the other way, we know the curve has to always be increasing, so as x gets bigger, the curve gets bigger, and conversely, as x gets smaller, the curve gets smaller. But again, for negative values of x, we follow this same pattern. It's kind of steeper, closer to the origin, and then it gets more and more shallow as you get away from the origin. And in theory, you kind of want to have this almost symmetrical because the derivative is symmetrical. And I think that's kind of it. You might want to be really explicit about noting that the curve won't ever actually hit a horizontal point. So you could use some dashed lines for that. So you could kind of effectively note on some asymptotes. We don't actually know the value of these asymptotes, but I guess it can't hurt to note that you know they exist. And that's pretty much what we can say about y is equal to fx, the curve y is fx. So really what we've done is we've, I guess, quite carefully taken note of what we can work out from this y is equal to f dash x, and then use that to work backwards to get to this curve. And you may have seen questions like this before, although it's also common that you might be given a curve and asked to sketch the derivative. That's another common thing you might be asked to do. But as this question demonstrates, you need to be able to work in either direction. You need to kind of go back to the fundamentals of what's going on with calculus to really understand how you can move in either direction without actually being given the curve. So it's quite a tricky question from that perspective, because it would be very difficult to do this if you didn't really have a good grasp of what's going on as you move from a curve to its derivative and vice versa. And that's pretty much it for the question, although it's worth noting, if you aren't familiar, you may not be familiar depending on where you are with your studies, but this curve here, this shape, this bell curve shape, is actually a very common curve that you'll see, particularly if you go on to study statistics at university. So a lot of degrees have some amount of statistics in them, and you'll inevitably encounter something called the normal distribution, and it follows this bell curve shape. It's not this exact curve, but the shape of it is in this bell shape. And as you move from what you learned is referred to as a probability distribution function, you can then go to a cumulative distribution function, which will always have this shape. So you may see them referred to as a bell curve and an S curve. This can sometimes be referred to as an S curve because it's kind of like an elongated S. And when I was doing work in financial modeling, we'd often encounter curves like this if I was doing some kind of stochastic modeling where I was modeling random variables that perhaps due to something called the central limit theorem, or even not, if it happened to follow this bell curve, often we'd be looking at the cumulative function, and we'd often refer to it, kind of what does the S curve look like. And so this question, whilst it's not expressly testing that knowledge, it is interesting to think about it because it's something that if you go on to university, you'll encounter much, much more. So that's a little side note. Hopefully you find that interesting. But I think the core to this question is really just taking what we can know from the derivative function and use that to kind of, in at least general terms, note what the underlying function would look like. So I hope you found that helpful, and what I'll do in the next video is I'll work through part 2 of this question. All right, tick boom.